determine if an existing electrical service is adequate, several steps must be followed. Firstly, calculate the total load. This involves converting all amperage ratings to 120 volts to establish a common baseline for calculation. For the existing dryers, the calculation is as follows: 8.5 amps times 120 volts equals 1020 watts, and 5.5 amps times 120 volts equals 660 watts. For the new dryers, the calculation is 19.8 amps times 120 volts equals 2376 watts. The total load for the existing dryers is 1020 watts plus 660 watts equals 1680 watts. The total load for the new dryers is 2376 watts times 10 dryers equals 23,760 watts. Secondly, estimate the general lighting load. Use a conservative estimate of 1 watt per square foot. Measure the square footage of the area being served, including the laundromat, car wash, and sub-panels. The estimated general lighting load equals the square footage multiplied by 1 watt per square foot. Thirdly, apply a demand factor. For general lighting and receptacles, a demand factor of 50% is typically applied. The demand factor calculation is the estimated general lighting load multiplied by 0.5 plus the total load. Fourthly, compare this result to the service capacity. The service capacity is 200 amps multiplied by 120 volts, which equals 24,000 watts. If the demand factor calculation is less than or equal to the service capacity, the existing service is adequate. Let's consider an example. Assume the laundromat and car wash area is 2,000 square feet. The estimated general lighting load is 2,000 square feet times 1 watt per square foot, which equals 2,000 watts. The demand factor calculation is 2,000 watts times 0.5 plus 23,760 watts, which equals 26,760 watts. Based on this example, the existing 200 amp service capacity of 24,000 watts is not adequate to support the new equipment, which has a demand factor of 26,760 watts. A service upgrade would be necessary. Additional considerations include checking local building codes for specific requirements on general lighting estimates, considering the possibility of future load growth or additional equipment, and consulting with a licensed electrician to verify the accuracy of these calculations and to make recommendations for the necessary upgrades. When assessing the adequacy of an electrical service, a comprehensive approach is essential to ensure safety and reliability. This process involves several key steps, each contributing to an accurate determination of the load requirements and the capacity of the existing service. The initial step involves calculating the total connected load. This requires a detailed inventory of all electrical equipment and devices that will be connected to the service. Each device's nameplate should be examined to determine its voltage and amperage requirements. These values are then used to calculate the power consumption in watts, using the formula power equals voltage times amperage. For equipment operating at different voltages, such as both 120 volts and 208 volts, it is important to convert all power requirements to a common voltage, typically 120 volts, to ensure accurate comparisons and calculations. After determining the wattage of each piece of equipment, the total connected load is calculated by summing the wattage of all devices. This provides a baseline figure representing the maximum potential load in the electrical service if all equipment were operating simultaneously. However, in most real-world scenarios, not all equipment operates at its maximum capacity at the same time. Therefore, the next crucial step is to apply demand factors to account for this diversity in usage. Demand factors are multipliers that reduce the total connected load to a more realistic estimate of the actual load that the service will experience. These factors are based on historical data and empirical studies of how different types of loads are used in various applications. For example, lighting loads, which tend to be relatively constant, may have a demand factor close to 100%, while receptacle loads, which can vary significantly depending on the usage of plugged-in devices, may have a demand factor of 50% or less. Similarly, motor loads, such as those found in air conditioning systems or large appliances, may have demand factors that depend on the frequency and duration of their operation. Applying these demand factors involves multiplying the wattage of each type of load by its corresponding demand factor and then summing the results. This yields the calculated demand load, which represents the estimated actual load that the electrical service will need to support. In addition to the connected load and demand factors, it is essential to consider any other loads that may be connected to the service, such as general lighting and receptacle circuit. General lighting loads are typically estimated based on the square footage of the area being served, using a conservative estimate of 1 watt per square foot. This accounts for the power consumption of lighting fixtures throughout the space. Receptacle loads are often estimated based on the number of receptacles and an assumed load per receptacle, which can vary depending on the type of occupancy and the expected usage. Once all individual loads have been accounted for and demand factors have been applied where appropriate, the total calculated load is determined by summing all the individual loads. This total load represents the estimated maximum load that the electrical service will need to support under normal operating conditions. The next step is to compare this total calculated load to the capacity of the existing electrical service. The service capacity is determined by multiplying the service voltage, typically 120 volts or 240 volts, by the service amperage rating, which is the maximum current that the service can safely deliver. The result is the service capacity in watts, which represents the maximum power that the service can provide. If the total calculated load exceeds the service capacity, it indicates that the existing service is inadequate to support the new equipment and a service upgrade will be necessary. A service upgrade may involve increasing the size of the service entrance conductors, upgrading the service panel, and potentially upgrading the utility transformer to provide additional capacity. However, if the total calculated load is less than the service capacity, it suggests that the existing service is adequate to support the new equipment. However, it is important to consider additional factors before making a final determination. One such factor is the potential for future load growth. If there are plans to add additional equipment or expand the facility in the future, it is prudent to account for this potential load growth when assessing the adequacy of the existing service. This can be done by adding a safety margin to the total calculated load, typically 25% to 50%, to ensure that the service has sufficient capacity to handle future increases in demand. Another important consideration is the condition of the existing electrical equipment. Older equipment may be less efficient and may consume more power than newer equipment. Additionally, older equipment may be more prone to failure, which can lead to power outages and other electrical problems. Therefore, it is important to inspect the existing electrical equipment to ensure that it is in good working condition and that it is not contributing to excessive power consumption. Finally, it is always advisable to consult with a licensed electrician to verify the accuracy of these calculations and to make recommendations for any necessary upgrades. A qualified electrician has the knowledge and experience to assess the electrical system comprehensively and to identify any potential issues or concerns. They can also ensure that any upgrades are performed safely and in accordance with all applicable codes and regulations. Furthermore, it is crucial to check local building codes and regulations for specific requirements regarding electrical service capacity and load calculations. These codes may specify minimum requirements for service size, demand factors, and other related aspects. Adhering to these codes is essential to ensure the safety and compliance of the electrical installation. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including load calculations and service requirements. The NEC is updated every 3 years, so it is important to refer to the latest edition to ensure compliance with current standards. Article 220 of the NEC covers load calculations for various types of occupancies, including dwelling units, commercial buildings, and industrial facilities. It provides detailed methods for calculating general lighting loads, receptacle loads, appliance loads, and motor loads. It also includes demand factors for different types of loads based on their expected usage patterns. Article 230 of the NEC covers service entrances, including the size and type of service conductors, overcurrent protection, and grounding requirements. It specifies the minimum size of service conductors based on the calculated load, as well as the requirements for service disconnecting means and overcurrent protection devices. Other relevant articles of the NEC include Article 430, which covers motor circuits and overload protection, and Article 440, which covers air conditioning and refrigeration equipment. These articles provide specific requirements for the installation and protection of these types of equipment, which can significantly impact the overall load on the electrical service. In addition to the NEC, local building codes may have additional requirements that are more stringent or specific to the local area. It is important to check with the local building department to determine if there are any such requirements that must be followed. When performing load calculations, it is important to use accurate and reliable data. This includes obtaining accurate nameplate information for all electrical equipment, measuring the square footage of the area being served, and using appropriate demand factors based on the type of occupancy and the expected usage patterns. It is also important to consider any future load growth or changes in usage patterns that may occur over time. Overestimating the load is generally preferable to underestimating it, as it is better to have a service that is slightly oversized than one that is undersized and prone to overloading. However, it is also important to avoid oversizing the service excessively, as this can lead to unnecessary costs and inefficiencies. A properly sized electrical service is essential for ensuring the safety and reliability of the electrical system. An undersized service can lead to overloading, which can cause overheating, insulation breakdown, and potentially electrical fires. An oversized service can lead to unnecessary costs and inefficiencies, as well as potential problems with voltage drop and power quality. Therefore, it is important to carefully calculate the load requirements and to select a service size that is appropriate for the application. In summary, determining whether an existing electrical service is adequate involves a comprehensive assessment of the load requirements and the capacity of the existing service. This process includes calculating the total connected load, applying demand factors, accounting for general lighting and receptacle loads, and comparing the total calculated load to the service capacity. It also involves considering potential future load growth, the condition of the existing electrical equipment, and consulting with a licensed electrician. By following these steps and adhering to all applicable codes and regulations, it is possible to ensure that the electrical service is adequate to support the intended load and that the electrical system is safe and reliable. The calculation of electrical loads and the assessment of service adequacy are critical aspects of electrical engineering and installation. A thorough understanding of these principles is essential for ensuring the safe and efficient operation of electrical systems in residential, commercial, and industrial settings. Moreover, continuous monitoring and periodic re-evaluation of electrical loads are important to adapt to changing demands and technological advancements. As new appliances, equipment, and systems are introduced, their impact on the overall electrical load must be carefully considered to maintain a balanced and reliable electrical infrastructure. Furthermore, the increasing adoption of renewable energy sources such as solar panels and wind turbines introduces additional complexities to load management and service adequacy. These sources can provide intermittent power generation, which requires careful integration with the existing grid and consideration of backup power systems. Therefore, a comprehensive approach to electrical load calculation and service assessment must encompass not only the traditional aspects of load management, but also the integration of renewable energy technologies and the evolving demands of modern electrical systems. In addition to the technical aspects of load calculation and service assessment, it is also important to consider the economic implications. An oversized electrical service can result in unnecessary capital expenditures, while an undersized service can lead to operational inefficiencies and potential safety hazards. Therefore, a careful balance must be struck between ensuring adequate capacity and minimizing costs. This requires a thorough understanding of the load characteristics, the potential for future growth, and the available options for service upgrades. Moreover, it is important to consider the long-term costs and benefits of different service options, including the potential for energy savings and the impact on system reliability. By taking a holistic approach to electrical load management and service assessment, it is possible to optimize the performance and efficiency of electrical systems while minimizing costs and ensuring safety. Finally, ongoing education and training are essential for electrical professionals to stay abreast of the latest codes, standards, and technologies. The electrical industry is constantly evolving, with new products, techniques, and regulations being introduced on a regular basis. Therefore, it is important for electricians, engineers, and other electrical professionals to continuously update their knowledge and skills to ensure that they are able to perform their job safely and effectively. This includes staying informed about changes to the National Electrical Code, attending industry conferences and seminars, and participating in continuing education programs. By investing in ongoing education and training, electrical professionals can enhance their expertise and contribute to the advancement of the electrical industry.